Yes, that is okay, right?
Yeah.
Okay. So to implement any digital electronic circuit, like as an analog electronics, we have to do some mathematical equations, using the mathematical equation to some calculations. Here also, to implement the digital electronic circuit, we have to follow some mathematical equations. Those are known as Boolean laws or Boolean algebra, or the Boolean algebra. So Boolean algebra is the mathematics of the digital system. It's simple like that. Here we sometimes have to give given logic gates, then we need to find out the expression for the overall logic gates. Sometimes we will given the logic expression, then according to that we need to minimize those expressions so that we can get the finalized Boolean circuit, right? So vice versa. So this is it can be an expression, it can be a logic gate. For example, there is an expression, we can easily simplify those equations. But to do that, we need to know some laws. That was known as Boolean's law. So these are the laws or the rules of the Boolean equation or Boolean algebra. So there are certain rules and laws that must be followed in order to properly apply the Boolean algebra. Few are known as rules and few are known as laws. At first, we saw the rules. So, just simple, if it is a 2-input AND gate or 2-input OR gate, so any of the input can be a 0. If any of the input of the 0 to the AND gate, output will be 0. So it is very simple one, right? So, but sometimes it will be necessary for us to get whatever you are given to the input, we are trying to get the same output, but you have an AND gate. So what we can do, we can just connect another input to the ground. So it will be 0 always. So whatever you give, the output will be 0. Simple. So, and if you want to put another input to the VCC, connect to the VCC, the first one, you connect that one input to the ground. That always output will be 0 for AND gate. For the AND gate, if you connect one input to the VCC, then it will give you the output of what? Whatever you give to the input. If A equals to 0, output will be 0. If A equals to 1, output will be 1. And whenever, if both inputs are same, it will give you the same output. So it's simple. A dot A equals to A. These are the few small rules that we need to implement when we try to minimize the large expression. That's why we need to know those things. Okay. This is another important. If we have two variables and one complement to each other, then output will be 0. A dot A bar will be 0. Okay. So this is also known as AND laws. And here it is very simple one. If A equals to 0, A bar will be 1. If A equals to 1, A bar will be 0. So it's an AND gate, so output will be 0. Okay. So these are all about the AND gates, rules in the AND gates. Then now, few rules for the OR gates. So if you have one input connected to the ground and you are using an OR gate, output will follow the input. So if A is equals to 1, output will be 1. A equals to 0, output will be 0. Opposite to the AND gate. And this is the truth table. For 1, A plus 1, that means whatever you give the input, output will be always followed to the VCC. So whatever the connection to the VCC, it will give you logic high, or according to the value of logic high. If you connect it to 2 volt, it will give you 2 volt. If it is connected to 5 volt, it will give you 5 volts. So A plus 1 will be always 1. And A plus A, addition of two variables of the same variables will give you the
Same variable.
So if it is 0 plus 0, it will be 0, 1 plus 1 will be 1. And that is the complement.
1.
If we have A plus A bar, it will give you 1. In case of A dot A bar, it will be 0.
0.
Okay. So these are the few rules of the Boolean. Now we'll look at for the Boolean's law. The first one is the commutative law. So the commutative law of a multiplication of two variables. It means A dot B is equals to B dot A. In what orientation you keep the input, the output will be same. A plus B equals to B plus A. So there is no change. The order in which the input is connected is not a matter. So sometimes when we use a distributive law to expand the expression, then maybe sometimes the variable can change, AB or BA. So we can use actually AB to BA, so that we can take a common in the next step. That's why it is known as a commutative law. So whatever the input is, we can change the position. A dot B equals to B dot A. And all of them can be proved by the truth table, because in the digital electronics or in the logic circuit, we have to confirm with the everything is exploding from the truth table. Okay. This is the commutative law for the addition of two variables. Previous one is for the multiplication. This is for the addition, right?
AND gate and
so AND gate and OR
gate.
gate. So this is the OR gate. So it is also true. A plus B equals to B plus A. And this is also true for more variables. If you increase the number of variables, it will be the same. Okay. Then the second law of the Boolean algebra is known as associative law. So this is the associative law of multiplication of three variables. That means if you have three inputs of variable A, B, and C, and you have the product of AB, then you give the output of AB to the next AND gate to get A dot B dot C. It will be same as if you give the B plus B dot C and then take the output and give it to the next AND gate to multiply with A. So it will have the same results, right? They have the same results. And we can see from the truth table also, it has the same result. Because if you have, so it is an AND gate, P will be 1 when both AB will be 1. Then when both AB equals to 1, P equals to 1, and this output will be 1 when both are 1. So you will get only 1 here, right? At the final stage.
Similarly, all inputs are 1.
All inputs are 1. Similarly, for this one, the truth table is like this one. We can see we will have 1 when all inputs are 1. So that means wherever in which order you give, they will have the same result. This is known as associative law. This is associative law for the addition. So here also you have a given two inputs A and B, two variables A and B to the OR gate. The output of this first OR gate is given to this second OR gate to OR with C, and output is this one. So if you OR to OR B plus C, that is another two variable, then give it to the output to the next OR gate to OR with the A, it will also give you the same results. That means whenever any input is 1, we'll get the all output is same. So in which way, in any way of circuit you design, you will get the same result. So these two are known as associative law. So we have the commutative law and the associative law. And this one is for the associative law, second one. Okay. So this associative law is also, we can done these things for XOR gate, right? For the XOR gate, you can also have the same result. That means A XOR B, and the output of A XOR B will give it to the next XOR gate, to the A XOR C, will give you the result. Okay. And this is for the A XOR, right? This is for XOR, this is for XOR B. Okay. So in the commutative law, we already see that if you interchange the two inputs, still they will have the same results. And this is true for NAND gate and NOR gate. Yes,
so this is XOR gate and this is XNOR.
XNOR gate, yeah.
Okay.
Bubble in front of the XOR gate.
Okay.
So this one is the XOR, here this is OR, this is XOR sign. Then we have a bubble here, this is XNOR. Okay. So this is for XOR and XNOR. So this is the commutative law. So this commutative law is also true for this NAND gate, right? This is the NAND gate and this is the NOR gate, right? That means A dot B bar is equals to B dot A bar. It will give you the same result. Or A plus B whole bar will be equals to B plus B whole bar. So that means they will have the same results. Okay. But these NAND and NOR gates are the commutative, but they are not associative. This is important. That means if you want to use the NAND gate and NOR gate, they will give you, whenever in which order you give the inputs, they will give you the same result if they are commutative. But if you want to take an output A and B NAND gate, then given to the C, to the second NAND gate, it will not be same result. That means it will not follow the associative law. The NAND and NOR gate will not follow the associative law. So NAND and NOR gates are commutative but not associative. So NAND operation of A and B followed by C is not same as the NAND operation B and C followed by A. It will not be the same.
Can you explain that more in detail?
Okay. So for example, if you take the output A and B, right? So what is the output of this NAND gate? Just do the multiplication. If we have
A into
so let
B.
me draw and help me to say. So this one, right? A and B. So A and B given to this one. So we know what is the NAND operation.
AB bar, yeah.
So what is the operation when it will be high or low? Anyone say? So AB bar and then C, right? So then it will be what?
AB bar,
AB bar.
then the whole
and
bar.
Whole bar,
Yes.
right? This one?
Yes.
Is it correct? So for this next one, it will be BC, right? Then BC, right? BC, so BC bar, then you are given to A bar. So it will be now BC bar.
BC bar, A whole bar.
So it's not C. So it will be more easy to understand if you draw the truth table now. If you the truth table for at first these inputs, see the final output here, and for the truth table for this one, you'll see they are not are same.
Match.
They are not matched. Okay?
They are not matched, but what's called commutative?
Commutative means you can interchange their order here.
Okay.
This is the commutative.
Got it.
But associative means you are taking from the output from the previous stage, then giving to the second stage. So if you interchange their input in that direction, it will not give you the same results.
Got it.
This is the associative. Okay? The distributive law is the similar as the normal algebra. That means you just multiply. So A dot B plus C, A added B or C equals to AB plus AC. A simple algebra or normal algebra. Okay? This is known as distributive law. So for example, we can just write down AB plus AC or ABC plus ABC. So why we need those rules and laws? For example, if you have just simple example, this one, you have an expression like this, it is equals to A. How we are getting it is equals to A? Because if you take a common A, it is 1 plus B.
1 plus B.
We already saw that if you have a 1 plus R, it will give you 1, right? Anything you are connected to the VCC, it will give you
1.
1.
It will give you 1. Because if A equals to 0, 1 plus 0, 1.
0, 1.
If A equals to 1, 1 plus 1 equals to 1. So that's why it's a, if you take common, then 1. So we can use, by using the laws and rules, we can simplify our expression, Boolean expression. This is the simple one. Distributive law again. So for example, if you look at this right hand side, which is A plus B into A plus C. So if you just distribute it, A dot A dot C plus B dot A plus B dot C. So A dot A means A. We already saw that.
Yes.
If two inputs AND gate have same input, it will give you the same output.
Same.
A dot A equals to. So then AC, then AZ. So this is this commutative.
Commutative.
Commutative. So BA, we can write down AB also. Same thing. Then
B
BC.
dot C.
Now we take a common A, it will be 1 plus C plus B. So 1 plus any inputs, it will be 1.
One.
So A into 1,
One.
BC. then it is A into 1 means A.
A
So
plus
this
A dot.
whole expression can be come down to this simple expression A plus BC. Okay? So this is the how. So we need to keep in mind those laws and those look so very simple, but sometimes it will be not easy to remember. So you have to remember those laws carefully, right? Sometimes it will get confused with the AND gate and OR gates. So be careful. This one is known as absorption law. That means you are actually reducing the expression. So here in the left hand side, so it is A dot A dot A dot B. So A dot A means A plus AB, then you take a common of A.
1 plus
So
B
1
is
plus
1.
B, 1 plus B equals to 1 A.
Okay.
So actually we are absorption. So absorbing the expression. That's why it's known as absorption law. Then we have this complement. If we have a double complement, it will give you the same result, the normal value. Because if you give it to the A to the inverter, it will give you A bar. Then if you give it to the second inverter, it will be a double inverter. That means it will become A as a normal input. So these are the few laws, and now I will just take a break. As I mentioned to you earlier, I'll come within 5 minutes to continue. Okay. Thank you so much for your attention. So this is the law. Then we go for the.
He's already.
Can you remember that?
Yeah.
Then we move to our next slide. It's a De Morgan's law. So De Morgan is a mathematician, and his theorem provides a mathematical verification which is equivalent to our NAND gate or the negative OR as well as NOR gate as the negative AND gate. So there are two basic De Morgan's law. So most widely used to simplify our Boolean expression, widely used and very important law. So one is the first law is this: complement of a product. Complement of a product of the variables is equals to the sum of the complements of the variable. That means A dot B whole bar it will be equals to A bar plus B bar. Complement of a product of the variables is equals to the sum of the complement of the variable. That means A dot B bar equals to A bar B bar. So A dot B bar, that means if we need to this one A bar plus B bar, what is this one? A plus B for the OR gate. Then the output of this OR gate will pass through the NOT gate. It will give you A plus B whole bar. Right? This is well. So what is the NOT gate? NOT gate will be AB whole bar. Thank you. AB whole bar. So this is OR gate plus NOT gate. That means NOR gate, right? Okay. So A plus B whole bar is equals to A bar dot B bar. So this is my De Morgan's first law, right? So we can implement these things simply by, we are thinking that we have an AND gate, then NOT gate, bubble AND gate, we can implement this A dot bar B bar. So we have a NOT gate first, A input, variable A is given to the first NOT gate, the output of the first NOT gate is A bar, output of the second NOT gate is B bar, then two inputs is given to the two input AND gate, and the output is A dot B bar. So this is the NOR gate to this. This is the first law. Okay. So this law is true for 3 variables, 4 variables, whatever it is. Number of variables, it is true for any number of variables. And this is the truth table. As I mentioned that in Boolean expression or the digital electronics, we need to prove it by the truth table. Everything will be easily proved by the truth table. Here is the truth table for this first law. So this is my AB, then it will be A bar and B bar. So 0, 0 will become 1, 1, 0, 1 become 1, 0, 1, 0 become 0, 1, 1 will become 0, 0. So A bar, B bar means this one, right? So 1 plus 1 dot 1 will be 1, 1. Any of the input is 1, 0, the output will be 0. So here it is 1. And FB will be opposite. That means 0 plus 1 will be 1, 1 plus 0, 1, 1, 1 will be 1. So it is A plus B whole bar, just complement of this A plus B. 0 will become 1, 1, 0, 1, 0, 1, 0. So you can see these two lines are same. So the first law is proved. Okay. So this is true for any of the inputs. The second law is the complement of a sum of variables is equal to the product of the complements of the variables. That means A dot B whole bar will be A plus B, A bar plus B bar. A bar plus B bar. So this A dot B bar means this NAND gate, output of a NAND gate. And here A bar B bar means if you give two input to the OR gate, after the inverting, it will give you A bar plus B bar. So here, this is the gate. And this is the truth table for that second law. That means the complement of the product will be equals to the summation of two complement variable, right? Complemented variable. And this is also true for any number of inputs. Any number of inputs. Now, I explain you the rules, I explain you the laws. I also have the Boolean. Try to practice these things. Example 1, example 2.
You want to solve it?
Yeah. Try to solve it.
Excuse me.
Can you see? I just try to give you the laws as well. You write down the equation, the first one. So if you write down the equation, I can make it large.
Just go back to the equation.
Okay. write down the first two questions here so that I can make it bold. So, okay. Do you have the answer for first one?
A bar B plus A bar C.
So the answer of the first one, A bar dot B plus C bar.
B plus C.
Everyone have the same answer?
Yes, sir.
Anyone have different answer? The answer of the first one is A bar dot B bar plus C bar. Sorry, B plus
B
C.
plus C bar, sir.
Sorry, B plus C bar. Okay. The answer of the second one?
It was three terms.
A bar dot C bar
A bar dot C bar
plus A bar dot B
plus A bar dot B
plus A bar dot B dot C.
B bar C.
Yes, sir.
All of you have the same answer?
B bar C.
So answer is, can you repeat?
A bar dot C bar.
A bar dot C bar.
Yes, sir. Plus A bar dot B
Then
plus
A bar B C bar.
A bar B dot C. A, sir. Sorry.
A dot B dot C.
B, it will be A,
A,
B bar.
B
pla-
bar, sir. B bar.
It will be B bar in the
C
last.
bar
Plus
A
A
bar
bar B
plus
A B bar
Sorry.
C. A B bar
So have the
C.
same answer?
Yep.
Yes, sir.
All of you?
Yep.
Good. What about the third one?
Doing it.
A B.
All of you have the same answer? A B? Good. The third one is the A B. Okay. Then this one, AB plus C into A plus BC. This is the solve it. Can you see this one? Just use the De Morgan's law, okay?
Yes, sir.
No need
Second
to
law.
use De Morgan's law, so no need to do for other laws to simplify. So apply De Morgan's law until you can apply. Keep applying the De Morgan's law.
Is this a new one?
Yeah, new one. This is the fourth one, okay? What is the result?
A bar plus B bar.
A bar
B bar.
plus B bar or A bar B bar?
A bar B bar.
A bar B bar
Plus A bar C bar.
A bar C bar
Plus B bar C.
plus B bar
C bar.
C bar.
Plus A bar B bar plus A bar C bar.
We have click on, then try this one now. A plus B, C bar D bar plus E plus F bar. What is the answer?
A bar B bar.
A bar B bar
Plus C plus D.
C plus B
Plus D. All multiplied by E bar F. How F? F is multiplied by E bar.
so C plus D I think, right?
Yeah.
Then E bar F bar
Have it whole thing multiplied by E bar F. Not
The
the C
A
plus
bar,
D.
B bar plus C plus D is all in one parentheses.
A bar sorry I got it. Whole thing. Yes.
Could we do the working out for this one?
So this one,
Yes.
this one is the result, this one.
No, for
And
the.
then second one is this one, the answer is this one.
How do we get there?
Which one?
To the second answer?
This one?
Yes.
So it is a De Morgan theorem, right? So if you see the De Morgan theorem here, so you can consider this one x and y. So x plus y will be, just take
X dot Y.
x plus y whole bar. It will become
X bar dot Y bar.
y bar. Right? Then again it will become a plus b. So a plus b will become this x plus y whole bar become x bar y bar. Something like that. So all of you have the result, or you want me to show you? All of you have the result?
Could you work it out?
Okay. So the question was a plus b, C bar D bar plus E plus F whole bar, right? So here, so we can make it A plus B C bar D bar dot E plus F bar whole bar. So this X and this is Y. So X is OR operation, then we go to AND operation. Here again we have OR AND operation. We can make it A plus B whole bar plus C bar D bar whole bar. And it will remain, this one will become E bar plus F double bar. Then if you break it again, it will become A bar dot B bar.
No, the last one becomes multiplication dot.
Which one?
The E plus F bar.
Mm-hmm.
When you apply enormous load, it becomes a multiplication. So E bar F.
E bar
Not
F.
plus F.
You are
Yeah,
dot F.
that's supposed to be a multiplication.
So it's
So-
X plus Y whole bar. E bar dot F,
Dot
sir.
Oh, sorry.
E bar dot F.
F double bar means F. Yeah, sorry, thank you. Then we have this one to here,
Plus
plus then this one also same. C double bar, D double bar. So double bar will become C, right? And double bar become D. Then we have the bracket here, full bracket here, then E bar F. So A bar, B bar plus C plus D whole bar E bar F. So I will upload this one, that will be easy. So because here my writing is very bad. Okay? So this is how we can simplify the Boolean expression by using the laws and the De Morgan's theorem. Okay? So try to practice from the reference book or anywhere, and I will also upload these things. Try to change the variables, try yourself. Your book. Okay. Then what else here we have? Okay. And then we'll go to our next slide, the last one for today. The NAND and the NOR gate are known as the universal gate. So how we can implement any of the gate by using this NAND gate and NOR gate, right? Because this NAND gate is known as universal gate, NOR gate. So I first look at the NAND gate. So that means we can implement any of these gates by using the NAND gate. We have OR gate, we have AND gate, we have NOR gate, we have NOR gate, we have XOR gate, we have XNOR gate. So we can implement any of the 6 gates by using the NAND gate. The first one is the inverter or the NOR gate. So inverter means whatever you give the input, it will give you the opposite output. If you input 1, output will be 0. If the input is 0, output will be 1. So how we can implement these things by using a NAND gate? So we already saw that if it is a 2-input NAND gate and if the input are same, the output will be the same, right?
Yes.
In the rules of Boolean expression, right? So A double A will give you A bar. So that's why. So if you use the same connection, same input to the 2-input NAND gate, it will give you the opposite output or the complement of the input. So that means to implement a NOT gate, we require only one NAND gate.
NAND gate.
Only one NAND gate. So AND gate using NAND gates. So what is the AND gate? AND gate means output will be the product of the 2 variables or the multiple variables. So this is the output. This is my NAND gate output A dot B whole bar, and we need AB. So you already saw that. So if it is the output of the NAND gate is given to the inverter, the complement will be removed, and you will get the AB. So in our previous slide, we saw that how to implement the NOT gate. So that means to implement AND gate by using NAND gate, we require 2 NAND gate. So there is the input AB, output of this first NAND NAND gate is the AB bar. Then if the same input is given to the second NAND gate, it will give you AB. So it is the output of AND gate. So we can implement AND gate by using two
Two
NAND
NAND
gate.
gates.
OR gate. So usually output of the OR gate is the summation or addition of two variables or multiple variables, right? A plus B. So what we can do here, we can implement, and this is my NAND gate. So we can use the De Morgan's law here, right? De Morgan's law. A dot B whole bar equals to A bar plus B bar. This is De Morgan's law. So that means if we give two complement input to the NAND gate, it will give you A plus B, right?
Plus B plus
So if we look from here, from the De Morgan's theorem, we can see A dot B whole bar. This is my A dot B whole bar. Then if we implement it, complement this using the NAND gate, it will give you the AB, A plus B.
So one NAND gate is enough.
So no. So here we need to apply inverter circuit. That means we have to have this inverter circuit.
Two
So
NAND.
that means we have to give the first input to first inverter and second input to the second inverter. Then output of this two inverter will give it to the two input NAND gate. Then we'll get A plus B. So we already saw how to implement this inverter. So that means we need three NAND gate to implement an OR gate. To implement an OR gate. NOR gate using NAND gate. So what is the NOR gate? Opposite of OR gate. So if the output of the OR gate is complemented, then it will give you the NOR gate. So I already saw how to get the OR gate.
OR gate.
To implement an OR gate, we need three NAND gates. Then output of that NAND gates will give to the second inverter or the next inverter, and we already know how to get the inverter circuit, right? So we need to know this inverter circuit. So this is giving me the OR operation. Then output of this one will give to the next NAND gate to input NAND gate. It will give you
One more.
NOR output. So here we require 4 NAND gates to implement a NOR gate. Okay. XOR gate. So what is the XOR?
If any
XOR is the when any
Input
output
is-
will be high when both the inputs are opposite.
opposite.
Right? A bar B plus A B bar. So this is how we can usually implement this one. So the A input is given to the inverter circuit, then the output of the inverter is given to the first AND gate, and then we also give the B input here. On the other hand, we give the input B to the inverter circuit, then output of this one, go to the second AND gate, AND gate. Then the output of these two AND gate is given to the OR gate. So this was the common one. But we are trying to implement this by using the NAND gate.
NAND gate.
So now we already know how to implement NOT gate by using the NAND gate, how to implement the OR gate by using the NAND gate, and how to implement the two input AND gate. So we require how many? So for NOT gate inverter we need 1.
One.
So 1 plus 1, 2. For here we need 2 each, right? So 2 NAND gate here, 2 NAND gate here. 2 plus 2, 4. 4 plus 2, 6. And to implement an OR gate, we need 3.
Three.
So total 9 gates we required.
For its call.
So this is how. But it is also possible to implement this AND gate by using 5 NAND gate. By using 5 NAND gate. It is also possible by using the 5 NAND gate. Okay? So because here this will be give you A bar, right?
Yes, yes.
So this is A bar B. A bar B whole bar. This is A bar and this is B, and the output will be A bar B whole bar. Here again, this is B bar, this is A B bar, and the output will be A B bar
A
whole bar. Now we have A bar B whole bar and A B bar whole bar. Then if you give it 2 here, that will be the complement. Then if you apply the De Morgan's theorem, it will give you the A bar B plus B A bar. So by using 5 gate also, we can implement this NAND gate. Is it okay? It is also by using little complex calculation, we can also implement this one by another way, by using 4 gates, 4 NAND gates. By using 4 NAND gates. This one I want to explain. Here, if you look, so this one I'm talking at first. We give it the A input here, and we give this to input A and B here, right? So output of the NAND gate, for example, okay, let me draw first. So this is A, this is B. So here we'll give AB bar, right? Okay. Now we are giving it this to this input. This is another NAND gate. So what will be the input here? It will be A dot AB bar whole bar, right? This is my input here.
AB whole bar.
AB bar whole bar, right?
AB whole.
So,
AB bar.
okay, yeah. So for example, this is X. Okay, this is my X. So here, this one, if I, this X equals to A bar, AB whole bar. If I apply De Morgan's theorem here, what I can write?
A bar plus AB.
AB. It's a De Morgan theorem. Okay. Then by using a distributed law, this same expression I can write down this way. A plus, for example, just for example, if it is A plus BC, we can write down this one A plus B into B plus A plus C, sorry, right? ABC we can write this way also. How we can write this one? If you just distribute it, A dot A plus A dot C plus A dot B plus B dot C. So A dot A will be A
plus A
then
dot
AC,
C, AB,
AB
BC.
and BC. So if you take common A,
1 plus C,
1 plus C plus B
B
plus
plus
BC. So that A into 1
plus BC,
it will become A plus
BC.
BC. Right?
Yes, yes.
So this expression can be written in this form as well. So if I try to write down this one as well, according to that one, we can write down A plus A bar into A bar plus
A bar plus
B.
B.
So it will give you the same result, right? So if you then distribute it, it will become what? A dot A bar plus AB
plus A
A
bar
bar
dot
A
A
bar
bar plus A bar dot B.
So A dot A bar 0
AB
plus AB
0.
plus A bar A dot bar A bar
Sorry,
A bar
A bar
plus A bar B.
B.
Then if you take a common of B here,
A
bar
plus A bar.
A plus A bar.
A bar.
A plus A bar means 1, right?
1.
So A bar
A bar plus B.
So here we'll get A bar plus
B.
B here. Similarly, have same expression here for this one. For this one,
B dot
we can write down here. Right here, it will be
B
A
dot.
plus B bar. Here A bar plus B, here it will be A plus B bar. So these two is given to the final NAND gate,
NAND
right?
gate.
the final NAND gate will have
A bar plus B
into
into
A plus
A plus B bar whole bar.
whole bar. Then if you draw it, it will give you the output. So this is how we can also implement the, so by reducing the number of NAND gates. At first it seems that we require 9 NAND gates, but it is also possible to implement it by 4 NAND gates. Then what we have, NAND gate. Okay. So then the NOR gates, right? So to NOR gates, XNOR gates, we just need to implement another NOR inverter, right? So it will give you the XNOR. We already have the XOR gate. So with the 4 NAND gate, we can implement XOR operation.
XOR.
With 4 NAND gate, we can implement an XOR operation. Then if you take
NOR.
the output and give it to the 2 input NAND gate,
NAND.
it will act like a NOR gate. It will give you the XNOR operation. Okay. Now the NOR gate as universal gate. Similar. So we can implement any of the gates by using the NOR gate. The first one as the inverter. So again, it will be the 2 input OR gate. If you give it to the 2 input OR gate, NOR gate, it will give you the output of the complement of the input. So to implement an inverter circuit, we need 1 NOR gate. Then if we go for the OR gate using NOR gate, so OR gate is A plus B. So that means if you give it to this A plus B OR gate, it will be A plus B whole bar. Then if you give to the output of this first OR gate to the next OR gate, to input OR gate, then it will give, sorry, NOR gate, it will give you A plus B, the OR operation. So to perform the OR operation, we need 2 NOR gates. To implement AND gate, what I need to do? So this is my AND gate operation, and this is my NOR operation, sorry. This is my AND gate, and this is my NOR gate. So we need to have this result, right, from here. So if you give to the inverter input to the NOR gate, we'll have this one. And we already know how to invert this input. So by using just inverter to inverter here, to implement to inverter, we need 2 NOR gates. Then output of this 2 NOR gate will be given to the 3rd NOR gate, and the output will be AB.
3 OR gate.
So AND operation,
NOR
to perform the AND operation, we need 3 NOR gates.
3 NOR gates.
To perform or to get the NAND gate using NOR gate, so this is the NAND gate operations, and if we implement the AND operation or not, it will be AB whole bar. So you already know how to get these things. We need to have to input 2 NOR gates, then will give it to the 3rd NOR gates, right? And that will be AB. Now you have to implement again a complement inverter circuit. Then you will give the
One more,
4th
NOR
inverter circuit or inverter circuit. Then it will be AB whole bar.
4 NOR gates.
So 4, yeah. So XNOR gate. So XNOR is the output will be high when both inputs are in the same, right? Either 0, 0 or 1, 1. So this is the AB, so we need AB bar. So AB plus AB bar, right? AB plus AB bar. So this is the inverter circuit to give you A bar, and this is the circuit to give you the B bar. It will give you to the 3rd NOR gate, it will be AB. And then if you give it to the 3rd bar, it will give you the A plus B plus C. So this is the thing. To implement this one, we have to understand that for example, so if you want to implement a 3 input operations, A, B, C, 3 variables, right? So we have a 3 variables here. We can give A bar and B, C, B plus C bar, then it given to, and we get implement this logic function. So to implement any three variables logic function or something like this, we need three NOR gate, right? Three NOR gate. To implement this one, A plus B into C plus D. A plus B, output of the NOR gate is A plus B whole bar. C plus D, output of this NOR gate is C plus D whole bar. Then you have given to this one, then if you apply the De Morgan's theorem, you will see the result. So A plus B into C plus D, to implement this one, we need three NOR
NOR
gates.
gates.
This one also, A dot B plus C also need three NOR
Three
gates.
NOR gates.
So whatever it is, every time, if it is the logic expression is something like that, every time we need three NOR gates. That means any Boolean expression which can be written in the form of A plus B into C plus D can be represented by
Three
three
NOR gates.
NOR gates. Okay, three NOR gates. So now, what we are trying to implement the XNOR by using the NOR gates, right? So here, this is my AB and this is my original output. We need this one, AB plus A bar, B bar. This is my XNOR, right?
Yes.
Okay, so if we consider A bar is equals to, so this AB bar, sorry, A bar, B bar is equals to P. Let's say. And this A bar, B bar, we can make a De Morgan's theorem by A plus B
B whole bar.
whole bar, right? So what does it mean? We can write down this one expression output of y is equals to AB plus A bar B bar, right? So now we are saying that it is AB plus y, sorry, P. AB plus P. So it can be written as P plus A into P plus B. The same expression is this one, right? Again, I'm saying it. So this is my goal. We have to reach here. This is the XNOR operation or XNOR expression. So here I just say that consider this A bar B bar is P. Okay, and this P is also true for the De Morgan's from A plus B whole bar. Okay, so if you consider A bar plus B bar equals to P, then we can write down Y equals to P plus AB, and P plus AB can be expanded
P plus
according to
A.
this one we already saw.
Yes.
So this is the expression we already saw. If any of the expression is like that, A plus B into C plus D, we can represent by three NOR gates. That means we can implement it by three NOR gates. So this is one. So P equals to A bar B bar, we already considered, right? So this is P plus A into P plus B. So if you write down P plus A and P plus B, if you give it to here, it will be P plus AB. So what is P plus AB? That means we have this AB and this A bar dot B bar can be implemented by one NOR gate. A bar dot B bar can be implemented any of the NOR gate. So this NOR gate, if you connect this NOR gate to here, like this, so this is P, this is P. From here we are already getting A bar dot B bar. Then if you go here, it will be P plus D. So it will be giving you A bar B bar plus AB. So for this P plus A or P plus B, P plus A into P plus B, that means for this kind of expression, we need three NOR gates. So at first we implement these three NOR gates. We already have P plus A into P plus B. Okay? So what is P? A bar
A
plus
bar,
B
B
bar.
bar.
So how we get this A bar plus B bar? We need another XOR gate.
Okay.
So this is the XOR, another, NOR gate.
NOR gate.
So this is the NOR gate. It will give you A bar plus B bar. So you just add this one. Then this P is actually A bar, B bar. So A bar, B bar. So this is how we can implement the XNOR by using the NOR gate. Okay. So what is the XOR? XOR is just complement of XOR, right? So it will become from here to here. So we need two. We have AB plus A bar B bar. We have what? A plus B bar plus A bar B. So if you want to complement, what you need to do?
We
you
have
just
to
add
add
one
more NOR gate at
NOR
the end.
gate, and it will give you the complement of the So this is all the logic gates, all the logic function. In next class, we will discuss about the K-map, kind of map, and the Boolean functions, SOP and POS. Everyone sign here today?